Well, maybe we'll just start with something less sophisticated and just go through it here. So I like this question a lot. Let me pull it up here. Okay, so let's just look at something like this. This will be a review of a rational function, which I didn't see on your test, but it is covered there. Do you remember how to find any of these key informations, key pieces of information, x, y-intercepts, horizontal asymptote, vertical asymptote, anything like that? Any of that?
I know how to find y.
Okay, how do you find the y-intercept?
You put 0 in for the x's.
X equals 0, perfect, and you get 3/2 because the negatives cancel.
Yeah.
For the x-intercept, you set the numerator equal to 0.
Right.
All right, so you just set x minus 3 equals 0, and you get x equals 3.
Yeah.
For the vertical asymptote, you set the denominator equal to 0.
Mm.
So that means that x equals 2. Now it's an equation. That's why I wrote it x equals 2 instead of just the 2 for that. All right. Now the horizontal asymptote depends on the degree of the numerator and the denominator. So the degree of the numerator is 1. The degree of the denominator is 1. When those are the same, and there's actually a couple of different cases, it's just the ratio of the leading coefficients here.
Mm.
So it ends up being y equals 1 over 1, which is 1.
Yeah.
Okay, there are no slant asymptotes. So to go about graphing this, you take the key pieces of information that we just found and you apply them to this graph. Okay, so I actually like to start with the horizontal and the vertical asymptotes. So the horizontal one's at 1, the vertical asymptote is at 2. Okay, and then we know there's an x-intercept at 3, a y-intercept at 3/2. Okay, and you said you have a calculator available to you, so you would actually see this there. Do you need us to go through how to graph on a graphing calculator, something like
No.
this? Okay. Now your class, your exam's way more sophisticated than this, so we need to talk about some other stuff. We need to talk about the domain.
Mm-hmm.
Okay. Now the domain is any restrictions? Are there any restrictions on this graph on the right?
No.
So what about this place where it goes from positive infinity down to negative infinity? So vertical asymptotes, they're problematic when it comes to domain. So they're excluded from the domain.
Okay.
So anywhere you see a vertical asymptote or a hole. Now when you have a nice polynomial like you had in your quiz, hey, no issues there. Okay. But this is minus infinity, excuse me,
Mm-hmm.
to 2 union 2 to infinity.
Okay.
So the range is sort of similar. The range is now going bottom to top. It goes down to minus infinity, but it's broken up by this horizontal line here, which is at 1. So it goes up to 1, but it doesn't touch 1, but then it goes from 1 all the way back up to infinity.
Mm. Okay.
All right, so now the end behavior, that's another thing that it asks for. So the end behavior, as x goes to infinity, okay, and what that means really means, like, literally it means tracing the curve to the right. So imagine you're tracing the curve to the right. What does it approach? To the right. What is the y value that it approaches?
Positive infinity.
That would be if it were up here.
Oh yeah, it
So
approaches.
it approaches this horizontal asymptote,
Yeah.
which is 1. And then we can also go the other direction as x goes to negative infinity. Okay, and I'll do that in blue here. That literally means to the left. You're going to the left side here. And it also approaches, which is 1. Now polynomials tend to go to infinity, but rationals do not. Excuse me.
Okay.
Is any of this unclear or confusing?
No.
Okay. So the next thing that's on your sheet there, we can talk about is intervals of increasing and decreasing. So increasing means up and to the right. Up and to the right. The graph is going up and to the right. And even though we talked about this to the left, to the right, you now kind of restart, way you look at it. So the graph on this top part is actually, I guess I can show this in green. I know there's a lot going on here, this graph, but it's actually all going up and to the right.
Okay.
Do you believe that? Do you see that?
Yeah. I see it.
Okay. But it's also going up and to the right here. Is that agreeable with you? Because
Yeah.
it's a little odd. So it's actually going up and to the right everywhere. So it's actually increasing from minus infinity to 2, union 2 to infinity.
Okay.
Now decreasing is going down and to the right. And it's typically either increasing or decreasing. So since it's increasing essentially everywhere, there's nowhere that it's decreasing. You could say empty set or no real numbers, things like that.
Okay.
All right, we've already answered the x-intercept, y-intercept, and some things like that. Okay, so I tried to give you something totally different than you saw in your quiz. Should we go back and do more of like a quiz question, or should we do the quiz question?
I think we should do a question like the quiz.
Okay, let me graph one that, excuse me, that see if I can get this to work out. Trying to pick something where the numbers are reasonable, nice, and I'm unsuccessful again. Okay, let's go 6. Okay, here we go. I've got one. You can see these are long questions. I mean, you're not going to get a bunch of these on your test. Okay, so this is somewhat like the one that you got on your quiz. The numbers are a little bit bigger, but and you said you're allowed to graph this. Is that, and that's totally okay.
Yes.
Okay, so let's do this. Let me go to Desmos and snip in the graph of this. And if you would like, you can graph it on your calculator, but all right, so let me frame this a little better. it goes down, minus 20. It's 200. Okay, yeah, this is a good window. Okay, so here's the graph. And actually I should have snipped in the, I'll get these nice points. Okay, so this graph, and this goes down forever. This goes down forever. All right, so let's just follow the order from your quiz here. So domain. This is nice and smooth and continuous everywhere. Are there any restrictions on its domain?
No.
No. So it's just like you said. Now you're using a set builder notation. You may want to switch to interval notation for this class. May save you some time.
Okay.
Range. So this is where it's a little bit tougher. So these go, how far down does this go? Do these arrows go?
Infinity.
Minus infinity, yeah. And then we need the max. So I didn't give it to you, but the max is here. Let me give you that value. 3.108 comma 40.994. So which value goes here in the range? Do you remember?
40.994.
40.994, yeah. Okay. So that's our range. Next question is end behavior. Okay. And let me actually grab this graph again. I'll make it a little smaller and we'll do it up here. So end behavior now. So we say as x goes to infinity, that means to the right. And like what I mean by that is you trace along the curve. Can you see my cursor here? You're tracing along the curve.
Yeah.
And you say, well, when it stops kind of going up and down, well, what happens? So how far down does it go?
Negative infinity.
Negative infinity. As x goes to negative infinity, and now we're going the other way to the left, what do you say about f of x?
It goes to 40.99.
To the left though. So left means you're going, you're tracing the curve all the way to the left, and then look, it eventually just goes down, 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 down.
Negative infinity.
Negative infinity, yeah. I mean, look, in full disclosure, this is not interesting. This like, analyzing graphs is not, it's like doing taxes or something. It's not interesting, but we gotta figure this out. We gotta find a way to do that. Now, this place up here, it has some other features. It is a max, and we'll get to that. But is this like as x goes to infinity to the right, as x goes to negative infinity to the left? Like, do you think you could replicate that on a test?
Yeah.
Great. All right. So now the next thing it asks for is the increasing intervals. So you need a little more information. I'm actually going to have to grab this graph one more time. Okay, so you actually need these 3 points here. This is minus 6 comma 0. This one is minus 1.608 comma minus 195.15. And I already gave you this one, but I'll write it again, 3.108 comma 40.994. And we want intervals of increasing. So increasing means it's going up and to the right. And you start from the very left. And so from minus infinity to minus 6, it is increasing because it's going up and to the right.
Right.
All right. But then you're going down and to the right. It's like if you're hiking, it's like you went uphill and now you're going downhill. But then what happens? It turns around and now you're going up and to the right again. You're again increasing. But then what about this next interval? Are you increasing or decreasing?
You're decreasing.
Decreasing. So now we can fill that part in. You're decreasing when you're going down and to the right. So that's the other interval. That's the -6 to -1.608. And then the 3.108 to positive infinity.
Right. I think I understand this part better than domain and range.
Okay. That's unusual because domain and range are usually like the ones that are much clearer. But we'll look at those in more detail in the next problem. But we got a few more things to go through here for this one. All right. So the next thing is, so I'm going back and forth between screens to get it. The next one is x-intercepts. Okay. If you were to graph these, you would see these values, I guess. Yeah. So -6 actually occurs twice. So it's a double root, -2 and -4. So those are your x-intercepts. Y-intercepts. Let me just put that up here. So your y-intercept, when it's in this form that you saw in your quiz, where it's just this long, horrible equation, it's just the last number. Because when you put 0 in for x, cancels. It's just that last number.
Okay.
All right. So the relative max, absolute max, relative min, absolute min, we actually need these numbers. Let me grab these and move the screen down a little bit so you can see it. Okay, so the easier ones are the absolute max and the absolute min. So the absolute max has to be the absolute largest, highest peak. Okay, what's the highest peak?
The 3.108.
Yeah, now the number you just gave me is where is the absolute max, but they generally want the y value, the 40.994. And that's the answer to what is the absolute max? And you're like, well, it's 40.994. The absolute min in this problem would be the lowest place. And keep in mind that these go down forever. So if it goes down forever, there is none. There's no absolute min. And you might say, well, hey, Matthew, what about these? What about this down here? Well, we'll get to that, but you can keep going down further.
Okay.
Is that clear? Or would you like an analogy to falling in snow?
No, that's clear.
Okay. Okay. All right. Now the relative max and the relative min, these are kind of more substantive because like it's like when you're at this position over here on the left, -60, like compared to your neighbors, you're higher up on the hill than they are, but you're not the absolute highest. Like if you look out your front house, you would see, oh yeah, there's a house that's even higher on the hill. But relative to its neighbors, which are the nearby neighbors, it's bigger. Okay, so we know that at 0 and see again, this is where it's I don't know what your instructor wants. I guess they want the ordered pair. -6, 0 is a relative max.
Yeah.
The min, same deal. Like down here, you're like, hey, I can't see anything, lower than me. Well, from where you are, that's true. But if you could get over the mountain, you would see that you could go a lot further down. Okay. And then I don't know if your course is covering this, but this point up here is also a relative max and the absolute max. So you actually also have to consider that one as well. So there's only ever one absolute max and one absolute min. There can be multiple relative maxes and relative mins.
Okay.
Okay. So maybe you said domain and range are still sort of frustrating you. Let me grab a snip of that second problem. Maybe we can talk about the domain and range on that, because that is the type of problem you would generally see, some domain and range issues. And then I'll make another one here if we got time for that. Okay, so the graph, if we were to just extend this, I think this is important to do, extend this. This graph goes up forever, it goes left forever. Like, all right, but it's like if you're traveling to the right, and this is how you want to look at domain, you're traveling to the right, you're a traveler, and you travel right here and you hit this endpoint here, you've got a problem. And your problem is you have to jump. Let me do that in a different color. You have to jump to get back on the graph. And that's the one type of discontinuity, is called a jump.
Yeah.
So it's discontinuous at 0 because you can't go from where you were to the next part of the graph without jumping. Okay, but now you're okay. You're like, all right, I'm back on the curve, traveling along, and you hit this little speed bump. Okay, but it's actually defined up here. So that's okay. That's okay, because there is a place that it's known. But you keep going, but you get to this endpoint again, and what do you have yet one more time? You have a jump.
Yep.
And that's bad. Jumps are definitely problematic. Okay. But again, kind of like over here, see how it's not filled in there, but it is filled in down there. All right. So jumps are bad, but if they're defined at one place or the other, then you're okay. Now you keep traveling along the curve and you feel like, okay, I'm doing okay. I'm doing okay. Well, you never get back onto this other curve. So this is an asymptote. We know that there is some sort of a vertical asymptote right there. Right. So in terms of your domain, I know it's a little confusing because we're talking about discontinuities. If you can jump and you actually get to a point, that's okay. See how, like, even though it's not filled in there up at 4, it is back there, it's fine. And then you get to this other hole, but because it's defined up there, you're okay.
Okay.
Similarly, when you get to here, okay, and you jump, you're okay because there's a point there. So the only problematic place here is 4. Everywhere else there is an output.
Oh, okay.
Okay. And
Yeah.
oh, this thing is glitching on me. So that's the domain. Now range is, a little bit different. Okay. It's min to max, or you can think like lowest to highest. All right. And maybe you can tell me what is the smallest y value that you see in this graph? What is the smallest y value?
Well, 0
Zero.
technically.
Zero for sure. Okay. Now like 0 is right here at the -2. This is a little weird. This is a very complicated graph that they've given you. But if you were to trace the -2 0 up, you get to 4. Okay. So it's at least good from 0 to 4. But wait a second. If I go back the other way, how far up can I go? How high does this go?
Oh, infinity to the
Infinity.
yeah.
So all this other stuff is like distracting.
Okay.
But you might say, hey, Matthew, well, what about at 2? It's not defined at 2. And I'm like, you're right. It's not defined at 2. But if you go over to the right, it takes on a value of 2 over here on this other curve, or it takes on a value of 2 on this sort of parabola.
Okay.
And this is not a good example for us to be doing, but this is yeah, that's what we got in front of us. Okay. So let me come up with another problem here where there's some more issues. So let me see if I can do this on. Now I'll just draw it here. Okay, so here is a hole, and graph's going like that, and then filling it in, and we're going up like that. We're putting in a thing like that, and then okay, so in my sort of I'm envisioning something like this again, which is very similar to what you already had. What you're looking for, excuse me, are places where the graph doesn't have any overlap. Okay, like the potential problem areas are at 1, 3, and 4. So what is going on at 1?
There's a jump discontinuity.
Absolutely, but is the domain, is it defined there? Is the domain
No.
okay?
No.
Yes, because at 1 it's 1. Its output is 1, just not up there. So yeah, then this is where, and this is from previous classes, it's okay at 1. Like let's say this function is, this whole thing is called f of x, f of 1 equals 1, and that's good. So the jump discontinuity is different than domain. And maybe that's what's unclear. There's your domain, and then there's continuous, and they're different. So maybe that's what you were thinking of. Like this is not continuous at 1.
Mm-hmm.
But the domain is defined there.
Okay. Oh, okay. Oh, I see it.
Yeah.
Okay.
And maybe that's what you're referring to. So it's not continuous. Same thing at 3. At 3, it is not continuous, but the function is still defined at 3 because f of 3 equals 1 again. But
Okay.
what's going on at 4? 4, we got some issues.
Yeah.
Is it defined at 4?
No.
Does not exist. And that is an issue for our domain. So our domain, let me move this out, because this will be this I think will solidify this for you. The domain is minus infinity to 4, 4 to infinity. Okay, it's continuous. Where is it continuous? This is where I think you're thinking, okay, it's minus infinity to minus 1, 1 to 3, 3 to 4, 4 to infinity, because each of those are breaks, but they're still defined in the domain because of that overlap. And if you're taking calculus, this is pre-calculus or is this calculus?
This is pre-calculus.
Pre-calculus. Okay. All right. If you do take calculus, you'll do more of this, but we'll just work on pre-calculus stuff.
Okay.
All right. Now let me just give you a brief reminder about discontinuities. There are two types of discontinuities. There are removable, and those are holes. And that's it. The other types, jumps, are the non-removable. So those are your jumps and your vertical asymptotes.
Is there not like infinite?
Yes, those are the vertical asymptotes. So I'm categorizing them by removable and non-removable. But I think your teacher is saying the types of discontinuities are holes, jumps, and vertical asymptotes. And then they're saying whether they're removable or not.
Yeah.
Okay. So if we go back to, well, let me actually grab this one again. So I think this will make more sense now that we've talked about it. This jump at 0 is not removable because there's no way to make the 4 go to the 1 or go to the 0. It's just impossible. You just can't do it. Okay. But the hole at 2 is removable because you could just fill in. You just fill that in and then you're happy. So think of the holes as literally like potholes in the road. You can fill those in. Okay. But these jumps, they're like bridges that don't exist, bridges out or something. Because when you're jumping, you just can't connect the two. It's just impossible. And this isn't like social media where they're like, hey, remove, 2 sticks and make the new figure. Like you can't move these things. They either join up or not. And then the infinite ones, there's 2 possibilities for the infinite ones. They either approach the same value, but that's still not removable, or they approach different values, and that's still not removable.
Got it. Okay. Okay, I got it.
Okay. Now, what else can we cover here in the time we've got left? Is there other problems you think would be worth doing? Anything from class you think that might be?
Oh, how do you find the period on a graph?
From a graph or a function?
Both.
Okay. All right, let's look at sine. Sine and cosine, they have a period of 2 pi divided by b. And you might be thinking, well, I've never seen that b, or it's been a while. B is usually 1 because there's a 1 in front of the sine and cosine in front of the x. Okay, so their period is generally 2 pi. So what you would get though is something like this. It would be like 4/3 sine 2 pi x minus 1 plus 3, something like that. It would say, what is the period? Okay, and there's a lot of distractions, but you just need that number in front of x. You just need that b value. So your period is 2 pi over b, or it's 2 pi over 2 pi, which is 1. So let me give you another one here. Let's say g of x equals 9 minus 5 cosine x divided by 4 plus 7 minus 21. What is the number in front of x? What is the b value?
1.
So your b is actually 1/4.
All right.
So I'm being deceptive, but that's how you might see it on a test or a quiz, right?
Yeah.
Might do that. So it's 1/4, and yeah, it's a fraction and a fraction, which that's bad. You know, but that could be possible.
Okay.
Okay, now in full disclosure, this is because secant, actually let me do it the other way. Cosecant is like sine and secant is like x. They share this same property. But which two trig functions did I leave out? Okay, tangent of x and cotangent of x. These have a period of pi divided by b. I didn't invent these things, but that's just the rule. You know, like we're just going to go with it. Okay. So again, you know, you would get something horrible. H of x equals 1 minus pi over 3 tangent of 4x minus 3, like that. And the period is pi divided by b. What is the b value?
Oh, 4.
B is 4. So there's your period. It's pi divided by 4. So all you have to remember to do this on a test or quiz is figure out, you have to know whether it's tangent or cotangent. And then you have to remember for tangent, cotangent, it's pi over b, but the more general one is sine, cosine, secant, cosecant. It's 2 pi over b.
Okay.
Okay. Now, you asked me a really important question. You said, well, hey, Matthew, how do I do that when it's a graph? So let's look at a graph here. Let's go, let me make one up here. I didn't like that. Okay, let me do it this way. Oh, it didn't like that either. Okay. So this is like a best case scenario for you when you're given a graph is to find the period. There's kind of 3 options. The first option is you want peak to peak. Okay, so this first one is pi over 6 comma 2. And then the second one is, what did I choose here? 5 pi over 6 comma 2. So when you go peak to peak, you look at the 2 peaks and you always do right minus left. So we're talking about the x values though. So it's 5 pi over 6 minus pi over 6. Which ends up being 4 pi over 6, which is 2 pi over 3. And that's your period. So what a period literally is getting back to the same place you started. Hey, I'm at the top of the mountain. And then I slide down, slide all the way back up, and I get back where I started. That's the period when you go from one place to the other.
Oh, okay.
You haven't seen that before, have you?
I remember seeing it.
You remember seeing this? Okay. It's been a
Yeah.
while. All right. So similarly, okay, I could give you valley to valley. So this is your second option. Here's another graph here. So another option is you can go valley to valley. Okay. You're starting at the bottom, you climb up to the top of the hill, and then you come back down and you're back where you started. And again, it's right minus left. Okay. And it's your x values. It's that 8 minus 4, which is 4. It's these values here. So more generally, though, you just have to return to the same place that you were given, that you started with. Like if you start at the bottom, you have to get back to the bottom. If you started at the top, you have to get back to the top.
Okay.
But here's what sometimes you get, and again, these are just awful examples of these things. Let me go. Let's go 5. I'm just grabbing another snip here, and then I'll. Okay, so sometimes this is the least helpful case. Let's make this a little smaller. So you don't have peak to peak, and you don't have valley to valley. But the third possibility is they give you half a period. They give you peak to valley or valley to peak. Okay, so again, what you do is that right minus left, 2 pi minus 2 pi, which is 4 pi. But that's only half of it, so you have to double your period.
Oh, okay.
Yeah, I know it's weird.
Yeah.
It's really weird. Okay. So it's actually a little easier for like the more exotic trig functions. So let's look at tangent and cotangent. Let's go. All right. Just grabbing a snip. I'll be right back. Okay, so this is either a tangent or a cotangent, and we know that because of the vertical asymptotes. That's one way we know. Okay. Now I've been helpful here. I've given you these 2 points. Okay. How far apart are they?
Oh, they're 5 pi.
And that's your period.
Yeah.
That's your period. So they almost have to give you, like, this is almost too easy because they just give it to you right there. That's why I tried doing the other ones. All right, so let me yeah, trying to think of what else here you can say. Okay, so let's just kind of summarize what we did in the lesson here. You're going to be given some sort of a function, and you're going to have to find all this horrible stuff here. So it's all like note card, Quizlet, x-intercept means this, y-intercept means that. Have we clarified the domain versus continuity? Like, do you see how this one, its domain is everywhere but 2, but it's also discontinuous at 2.
Yeah.
And that's because this one's rational, so it's kind of an awful one. This one it has domain everywhere, and it's also continuous everywhere.
Yeah. Okay.
So it's only where there's sort of these like jumps, holes, and vertical asymptotes where you really got to start considering, domain and range being being different.
Okay.
All right. So hey, Paige, I'm still doing in person. I know it's been a while. If you think I could better help you that way, please let me know. I've got some limited availability for that, but if you like the virtual format, we can keep doing that as well. So just let me know. But I'll send you the notes and a link to the screen recording here shortly, and that is it for tonight.
All right. Thank you.
You're welcome. Good luck on your test. Let me know if I can help you again.
Okay.
All right. Bye now.
Bye.